So welcome again back to warped spaces, and we are here to listen to the third and last lecture by Professor Randall, please.
Okay. All right. So for this lecture, it's going to be a little. We've talked so far about signatures, primarily at the LHC. We talked about resonances. We talked about black holes, or what's really going to be more likely compositeness effects. And so in this lecture, I want to talk about flavor, and if we have time, some words about CP symmetries and asymmetries. I think what I want to try to argue in this talk is that, so we know that our S-warp geometry can solve the hierarchy problem, and I think it does amazingly well at giving us some insight into flavor physics as well. And a lot of what I've learned about this is from Gilad Perez, who's here, and some of this work is done with him, and also with Liam Fitzpatrick and Clifford Chung. And so here I have a slide that illustrates quite well how important flavor and symmetries are, in particular with respect to coffee. Okay. So I think it's fair to say that, I mean, certainly here in this audience, a lot of people are thinking about the weak scale, and I'm forgetting how to do this. So there's a lot of attention to the weak scale, but I mean, for those of us who've been in the field for more than 5 years, you know that flavor and CP have always been outstanding problems. I mean, they're really important things to understand as well. We don't have that many unexplained phenomena in the standard model, but the standard model works very well. The things that don't work so well is understanding basically masses. So the hierarchy problem is the big problem. Why are masses what they are? Why is the overall mass scale? But what explains the really intriguing and bizarre combination of quark and lepton masses and mixing angles? I mean, that is really a mystery at this point in the context of the standard model. And it could be the parameters just are what they are, but it could be that there's some underlying explanation. And it's worth exploring that and seeing whether it's possible. And what's interesting is, of course, that almost any theory of weak scale physics has implications for flavor and CP. Once you change the Higgs sector, you almost necessarily will introduce new ideas about how flavor physics and CP violation come about. The problem is that usually the consequences are bad. The standard model does incredibly well, at least at preventing flavor-changing neutral currents, because of the Jim mechanism. Because the only flavor-violating parameter, that is to say the only parameters in the standard model that distinguish among generations, are the quark and lepton masses, essentially. Almost any other model is going to have new physics with new low scales, and it almost always gives you new interactions that distinguish among the generations. So that's usually a bad consequence of having low-energy weak scale physics. And in fact, as those of you who've worked on supersymmetry or any theory of the weak scale know, one of the real challenges is getting the electroweak sector, the Higgs sector, right, while simultaneously not introducing bad features into the flavor physics, not introducing flavor violations that we don't want. What I want to talk about today is turning this into a virtue, the fact that we can have new ways of addressing weak scale physics that might actually help us understand flavor physics and even explain some of the parameters. So maybe some good consequences of having some new weak scale physics. And I think it's worth thinking solutions in the context of models and field theory. And one of the interesting things is this is a problem that I think if string theory is really going to connect to standard model physics, eventually we want to understand the physics of flavor there as well, and a lot of the times that will be in the context of the wave functions in the bulk, similar to what I'm going to talk about today. And the other reason to think about this is, of course, no matter how obscure this problem is, it will not be a problem that has anthropic solutions. I mean, I don't think anyone can argue that the top mass couldn't have been slightly different, or that strong CP couldn't have been 5 orders of magnitude bigger, and anything about what we see would have been destroyed. I mean, this is clearly a problem that if it has a solution, it's going to be a real mechanism solution, a real genuine particle physics solution. It's not going to be an anthropic solution. So I think that's another reason that's really worth looking at. Okay. Now, geometry and flavor. Okay, so we've been talking about warp geometry, but in general, higher dimensional geometry is promising for explaining hierarchies. I mean, as we've argued, warp geometry provides multiple mass scales. That is to say, we said that each mass scale depends on, the relevant mass scale depends on where you are in the fifth dimension, and it depends exponentially on the distance. But there's a different mass scale at different places in the bulk. Furthermore, even in the context of flat dimensions, but particularly in the context of these warp dimensions, exponential hierarchies are natural. So mass ratios that we think are enormous from the point of view of just taking the ratio are much less enormous if we take a logarithm. So the fact that we get these exponential hierarchies is very compelling when we see that these big ratios of masses. And for this reason, extra-dimensional geometry has the potential for explaining flavor. In particular, I've been emphasizing that's one reason to consider putting fermions and gauge bosons in the bulk, or not that we put them there, but maybe they're there. If we have fermions and gauge bosons in the bulk, there's a potential for explaining flavor because the wave function overlap is what's going to determine the Yukawa coupling. So there's conceivably a geometric explanation for why masses are so different. And we have this exponential dependence on the bulk mass parameter that I mentioned, so you don't need large ratios. And the other thing that makes this really interesting, and I think this is a really big selling point that can't be emphasized enough, is that angles are necessarily connected to masses in a very suggestive way in these models. And it's so suggestive that I think it really makes me believe there could be something going on here that's really worth paying attention to. Okay, so what I want to do in this talk is just elaborate on flavor, describe the potential flavor in strong CP issues, and show how we might solve them, and ask questions about how well we can do. And if we have time, I'll talk a little bit about a solution to the strong CP problem in this context as well. So this is just a reminder of what RS1 is. We have the Planck brane, the TV brane, this exponential hierarchy. We have this metric that has this warp factor involving this parameter k. RC is the distance between the two. Here we have theta. Sometimes we use y as the coordinate. K is order and Planck. And it's natural to have electroweak symmetry breaking, okay, at the right scale. So we have the question, where are the fermions? And we've gone over this in the last lecture, the last two lectures, in fact. Only the Higgs needs to be on the brane, that is to say the weak brane, to satisfy the hierarchy. Light fermions on the brane, you can satisfy observations with minimal flavor violation like in the standard model. The problem if you have light fermions in the brane is you're not explaining flavor. And also, precision effects are ultraviolet sensitive, and they're not calculable. With bulk fermions, you really can possibly explain flavor in the way that we've started to talk about. But you can't hide flavor violation. You can't just say it's minimal flavor violation. You really have to think about what's going on. Well, see, naturally you get next to minimal flavor violation primarily through the third generation, which is almost good enough. So this really is quite interesting, and it's worth investigating what's going on. Okay, so let's just go over the basic idea, and then we'll elaborate more details, okay? So the basic idea we've already mentioned, but I'm going to go over it again. So when the fermions are in the bulk, that is to say in the five-dimensional space in this case, you expect to have non-trivial wave functions, non-trivial profiles for these various quarks. So for the light quarks, it's very natural to imagine that they are localized far from where the Higgs sits. The Higgs sits here on the TeV brane. If the light quarks are localized here, their Yukawa coupling is naturally suppressed by the small wave function over here. So a natural explanation for why the Yukawa coupling is so small is that the wave function associated with this light quark is so small over here. Whereas for the top quark, a natural explanation for why it's heavier is that it's localized over here. So again, the wave function overlap might be bigger over here. So for heavy quarks, we would expect them to be localized here. That is to say the top quark. For light quarks, we expect them to be localized there. And what determines this shape is simply the bulk mass parameter. What is the mass of the five-dimensional quark in the bulk? And it's as simple as that. And you can solve the equations of motion. This parameter z is just the exponential of phi. And so you can solve the equation of motion for the wave function, this is a parameter nu, which is m over k. So sometimes I'll refer to nu. And we find that simply where it's localized depends on if nu is less than minus 1/2 or greater than minus 1/2. If it's less than minus 1/2, you have the wave function localized away from where the Higgs sits. You have a light quark. If it's greater than minus 1/2, you have it localized where the Higgs sits, and you have, for example, the top quark. And you also see that it really is exponential, so that you have natural hierarchies from small deviations in m over k. Okay? So are there any questions on that? That's key to everything we're doing. Okay. What I want to say in the next slide, which is this kind of surprising but very interesting result, is that angles are also natural in this context. That's to say, the mixing angles of the standard model that we know and completely don't understand have sort of a natural explanation in this context. So let's try to understand that. So we can assume that the 5-dimensional mixing matrices are anarchic. That is to say, the Yukawa coupling for the 5-dimensional fields can just have order 1 entries all over the place, okay? Or it could be a 4-dimensional Higgs, but either way, there's no small parameters assumed. You just have order 1 entries in the mixing angles, okay? But what the actual Yukawa coupling is, isn't the Yukawa you put into the Lagrangian, this parameter v, but it's that parameter times the wave function where the Higgs sits, which in this case is the TeV brane. So the actual Yukawa coupling is not just what you put in, but it's f for the left-handed fields. This is the wave function for the left-handed fields evaluated on the TeV brane, times the Yukawa that you put in, times the wave function for the right-handed field on the TeV brane. Is that clear to everyone? Okay. That is the actual Yukawa coupling that we're dealing with. Okay? So although the V's are of order 1s, remember these F's are wildly varying depending on whether your field is localized on the UV or in the IR. So now we can just take YY dagger to find what the mixing angles are. We can diagonalize it by taking YY dagger and Y dagger Y. But when the bulk mass is diagonalized, FQ is diagonalized with eigenvalues FQI. And what you find is that the angles are very naturally FQI divided by FQJ. Okay? So let's remember what these F's are. These F's, again, are the wave function of the particular generation on the TeV brane. Remember that the masses are going to be proportional to FQ left, FU right, for example. So these are sort of naturally of order the square root of the mass divided by V, right? Because the masses related to the Yukawas are naturally going to be the product of FQ and FU. So a very natural thing would be for FQ to be of order the square root of the mass. What this tells you is that the mixing angles are naturally connected to the ratio of the wave functions, which are naturally connected to about the square root of the ratio of masses. Okay? So we naturally get mixing angles scaling as the square root of the masses. And furthermore, the angles, of course, thereby aligning with the mass structure, which is one of the very interesting and unexplained features of the standard model, right? We have this mixing matrix that's kind of the identity. We have big mixing between the first 2 generations, much less mixing between the first and the third generation. And we don't really understand why that is. In this context, this naturally comes out because everything is happening just because of the wave functions. The wave functions are determining both the masses and the mixing angles. And of course, there's some flexibility, there's some fudge factor, how much mass comes from FQ and how much comes from FU. But just qualitatively, this really has the ring of truth, right? It's doing the right thing with respect to angles relating to the masses. Okay? That's a very important feature, which I think is really compelling about these models. Are there any questions on that? Yep. The wave functions are a function of the bulk mass parameters. And we are assigning the bulk mass parameters in order to give rise to the correct masses. It's not a tuning because very naturally some number near 0.5 is going to give us most of the masses that we see. But once we've assigned those and have deduced what those F's are associated with those bulk mass parameters, and we've put them in precisely to get the masses to work, we find the angles naturally come out about right. Okay? Are there questions? Okay. So flavor from the bulk looks pretty good, right? We get masses hierarchically, exponentially. So that looks good. Angles are connected to masses in the way that we like. That's a really compelling feature. But of course, what about flavor violation? That's always the problem when we try to make an actual model of flavor. If you don't just put in the Yukawas, you generally have additional flavor violating parameters, and those can be dangerous. Those can give rise to flavor changing neutral currents or other effects that we don't observe. So it seems quite dangerous because here we have entire functions that are violating flavor. That is to say, these wave functions in the bulk are all flavor violating parameters. You don't just get the Yukawa on the TeV brane. You have the values of those functions everywhere in the bulk. And furthermore, those interact with the KK modes, which of course exist everywhere in the bulk. So the danger is that there can be KK mode interactions which are not proportional to Yukawa couplings, which thereby introduce additional flavor violating parameters. So it seems naively extremely dangerous. And the amazing thing is that it's not nearly as bad as you'd expect. And the reason for that follows from something we talked about in a different context already, which is this fact that the gluon KK mode is peaked near the TeV brain, as we anticipated. We've talked about this a lot because we talked about the phenomenology of looking for this KK mode. But it's peaked on the TeV brain. But remember this fact that we had this really flat section with a value of about 1 over the square root of the volume. Remember, this was about 0.2. But the key point here is that the KK mode is extremely flat. Okay? So independently of the shape of the wave function, as long as it's concentrated in the UV, you don't introduce additional flavor violating effects. For the same reason the gluon coupling is universal. It's completely flat. So as long as the wave function is concentrated here, you don't have flavor violation from this region. Okay? That's an amazing feature that is really a feature of warp geometry, that this gluon KK mode is mediating much less flavor violation than you would expect. Okay? Because of the fact that they're flat in the UV. Okay? So what that means is that if you look at some diagram like this, you exchange a KK mode. This KK mode, in general, will not introduce flavor violating things from the UV contribution, because when we diagonalize the masses, we also diagonalize this interaction as well, because this KK mode was flat. Remember that the source of flavor violation would have been if it wasn't flat, so it interacted with the different fields differently. But because it's flat in that region, it interacts with all the fields the same way. So the worst contribution isn't there. It's not quite as good as that, however, because there is an IR contribution. Because in this region, of course, this function is not flat. Now remember, of course, the light fields are localized here, but we know that those light fields mix with the heavy field, namely the top. Okay? We know that there is a non-trivial KM matrix, so we can't just isolate the light quarks. We have to take into account the fact that they mix with the third generation. And so all the flavor violation will come through this mixing with the third generation, which is why we call it next to minimal flavor violation. So if it had not been for the top quark, it would have been completely universal. But because the top quark is indeed there, and the wave function is, of course, changing quite rapidly in this region, we have to take that into account. Okay? So there is this IR contribution, that is to say, a contribution from near the TeV brain. So there's no flavor violation from the UV, but there is this flavor violation because of the mixing into the top quark. And so that's what we meant by NMFE, and when we diagonalize it, we do get some contribution, and that contribution will have to do with the mixing into the top sector. So if the two worst constraints you get, so the constraints are amazingly safe. There's two that aren't as safe as you would like, and those are both involve CP violation, which may or may not be significant. One of them is from epsilon K, KK bar mixing with CP violating parameter. It constrains this KK scale to be about 8 TeV. So, and that comes from the left-right contribution. And the other is strong CP violation, which I'm trying to get this notation to catch on, but it hasn't worked yet. But I'm calling it the little CP problem. So what do I mean by the little CP problem? Well, suppose you solve theta bar to 0 through some axion mechanism or whatever, but you have additional weak scale physics. You almost always get a direct contribution to the neutron electric dipole moment, even if you set theta bar to 0. And that comes about, in this case, from a loop involving KK modes. But in general, as you know, in supersymmetry, if you have A and B parameters, you have to tune a phase to be about 10 to minus 2 or 10 to minus 3. There's usually a one-loop contribution to CP violation, even if you set theta bar to 0. Okay? And so that I'm calling the little CP problem, which exists in almost any model of weak scale physics, including this one. And if you include this one-loop contribution to the neutron electric dipole moment, assuming the phases are there, you would get a strong constraint on the KK mode mass, 10 to 15 TeV. Remember, we want these KK modes to be about a few TeV. So this is a little bit high. I mean, you might get away with it by having some small tuning of parameters or something like that. But to get it natural, we'd like to have the scale to be a little bit lower. So the upshot of all of this is that you do amazingly well with flavor. You explain masses, you explain angles, and you satisfy almost all flavor constraints. But you have this small constraint in the CP violating issues, namely epsilon K, and the neutron electric dipole moment. Okay, that's basically doing no work. Okay, that's where you are. So now in this talk, what I'm going to do is do a little bit more work and show that it's pretty simple to get this KK scale, at least according to flavor constraints, down to a few TeV. And if we have time, I'll also talk about the strong CP problem, but I don't think I'll have that much time for that. Okay. Any questions at this point? Okay. So this is work that I did with Liam Fitzpatrick, Gilad Perez. And the question we asked was, can we do better than this generic case? Can we do a little bit better? Can we get the KK scale down from 10 TeV to a few TeV? What would it require? So let's just consider why we had so much flavor violation. Not that we had a lot, but why did we have it? Well, remember in the standard model, there's two flavor violating parameters, namely matrices, y up and y down. That's it. So remember, if you just have ups, you can diagonalize this. If you just have downs, you diagonalize that. It's only when you have both up and down that you have to introduce a CKM matrix and you get some flavor violation. Okay? In this case, we have more flavor violating parameters because in addition to the Yukawas, we have these mass parameters, which I've changed notation from M to C, but these mass parameters are C for both the up and the down right quarks, and also for the left-handed quarks. These are the bulk mass parameters. So we have Yukawa couplings of those fields to the Higgs. In addition to that, there are flavor violating parameters, which are the bulk mass parameters for the three types of fields, the left-handed fields, the left-handed doublets, and the upright and the downright. Okay? And that's why we have too much flavor violation, because we have more flavor violating parameters. In the standard model, we only have two. So what we did is we asked the question, can we actually get away with having something like a GIM mechanism here? It's only from a five-dimensional point of view. But basically what we said is assume that y up and y down, the Yukawas to the bulk Higgs, are the only flavor violating parameters. Okay? So what that would mean, according to the flavor structure of the theory, the flavor symmetry structure, is that these bulk masses would have to be combinations of y up dagger, y up, in the case of CQ, y up dagger, and y down dagger. There's actually identity contributions, which I have omitted here, but should be there, in fact, at the end of the day. But the point is there are no independent additional flavor violating parameters. These C's, remember, y up just transforms like L, y, R dagger. C transforms like this is R, y, L dagger. This just transforms like R, R dagger, R, C, R dagger. So these two have the same symmetry properties, which is why we can write it this way. And CQ, because it's left-left, involves both y up dagger, and y down dagger. Okay? Now let's think about this for a minute. Suppose this parameter R was 0. Suppose R was 0. How much flavor violation would we have in the down sector? Well, if R were 0, then if we look at C down, it's just y down, dagger, y down. If we look at CQ, it's just y down, dagger. So once we diagonalize y down, we will have diagonalized all flavor parameters for the down quarks. All of that will be diagonalized. So in the R to 0 limit, we will have absolutely no flavor violation in the down sector. Okay? Is that clear? The only reason you get flavor violation is because there's a small piece, if R is small, of y up dagger in CQ. So to the extent that R is a small parameter, we will have suppressed flavor violation in the down sector. We're not suppressing flavor violation in the up sector at all, but in the down sector, a small r will suppress flavor violation. Okay? Are there questions on that? I think there's a question somewhere. Okay. Okay, so what have we gained? Well, this R to 0 limit means that exactly no flavor violation in the down sector. So we're going to do a lot better in epsilon k because we're now suppressing epsilon k through this parameter R. Okay? With CP violation, it turns out that having only these two Yukawas means there's only one phase, and that's going to help there too because we're not going to get it at one loop, but at two loops. So despite the fact that we use this anarchic Yukawa, we're going to have the same flavor structure we had before, just like before. The key thing for us was that we have fewer parameters in the theory. Now all we have is y up and y down. We don't have y up, y down, CQ, C up, C down as independent parameters. There are only these two matrices, y up and y down. So it's a little bit non-trivial to check that you can actually solve for it and get all the masses and angles to work. But the fact is that you can. And the interesting thing is that this has the added advantage that it can be probed with precision top quark measurements. Okay? So by doing precision measurements, we have a chance of probing this structure. Okay? So we not only get all the nice things we got before, the masses and the mixing angles, but we're going to actually suppress these effects down to the point where just from flavor alone we could have a low scale of a few TeV. So this is just determined by consistency relations, and it turns out R is naturally of order 0.3 in a lot of the solutions. Okay, so let's just check what this does for flavor changing neutral currents and the electric dipole moment. Well, flavor changing neutral current in the kaon system will be suppressed by R squared, and it's going to be enough to lower the KK scale down to a few TeV. And furthermore, the electric dipole moment is going to be suppressed because there's only one phase. So we're just going to solve those two problems that's where we're nagging us, and that's it.
May I ask a question?
Yes.
So you said that you're suppressing the down sector but not
Right.
First, what does happen with the DD bar mixing?
So DD bar mixing, it turns out that it's sufficiently safe in this model. And that's because a lot of the, you see, all the flavor violation in these models is going, in some sense, it is going through the light quark, so the light quark mixes into the top quark. And in this case, it turns out it's safe enough. The interesting prediction, or the interesting effect, could be in CP violation in DD bar mixing, where we would naturally expect more than in the standard model. One thing we haven't yet looked at, which would be interesting to understand, is delta C equals 1 processes. And I don't know if they're, I don't think we're going to be ruled out by anything, but it would be interesting to see if there are interesting predictions with respect to the C quark sector. It will be very interesting to see that. Okay. Okay. So this is just to say that the electric dipole moment is only generated at one loop. This is a fancy argument that says that the simple argument is simply that all there is y up and y down. Therefore, there's only one phase in the theory. So if I write down a wine loop diagram, I'm going to get that phase and its complex conjugate, and it's going to go away. And it's only at 2 loops that you're going to get any strong CP. And then you've already suppressed this little CP problem by enough. Okay? So that's what's going on here. And this is a comment about possible signatures of this model. At low energy, we've solved the problem in the down quark sector, but DD bar CP violation might be bigger than it is in the standard model. It's going to be interesting to look at penguins versus tree level effects in various delta F equals 1 processes. At high energy, one of the really interesting consequences to this type of model, because you do have more flavor violation in the up sector, is that you could actually imagine seeing flavor changing top decays at the level of few 10 to minus 6, maybe 10 to minus 5. So that will be an extremely interesting thing to look for to test any of these models, will be flavor changing in the top sector. And of course, at high energy, we have all the kind of signatures we talked about in the last lecture. For example, the KK gluon decaying into tops, and maybe these other modes. Okay? So there would be lots of indications if this is the type of model that's going on. Some of them are sort of flavor independent, but this type of thing really relies on the flavor structure that we have here. Okay, so that's all I wanted to say about this particular model. Are there any questions about that? So what I'm trying to convey here is that not only do we have this natural explanation of the hierarchy, but we also are getting this natural explanation of flavor. We have these small changes in the bulk masses giving us the huge hierarchy we see in the quark masses. We get angles connected to masses. And we have sort of a Jim mechanism in the sense that this small r reduces the severity of flavor changing constraints, allowing us, according to flavor, to have a really low KK scale and really get away with it. And I think there's still some interesting work to be done to see which are the flavor violating effects that still might happen at levels beyond the standard model in this sort of scenario. Okay. So any questions about that? So I don't know that we can necessarily say better, but I want to present a model now that has even more Jim structure in it. But really, the reason I want to look at this is that I want to just point out that extra dimensions at least offer the possibility of having a new solution to the strong CP problem. So this is a somewhat more technical thing than anything I've talked about yet. But it's rather interesting to see that there's some additional structure, some additional possibilities in the context of these higher dimensional theories. So I want to do this in the context of spontaneously broken CP. So actually, I should probably check first. How many people here do not know what the strong CP problem is? Okay, good. Okay, so I can assume everyone knows what the strong CP problem is. Okay. So usually so there aren't that many solutions to the strong CP problem. People have talked a lot about axion models, and the other possibility that people talk about is spontaneously breaking CP. Okay? So why should we look at additional solutions? Well, one is that there really aren't that many solutions. And the strong CP problem, of course, is the fact that we see CP violation in the kaon system, in the B system, but we don't see it in the neutron electric dipole moment. And it's an incredibly small number, right? It's been measured at the level that the CP violating parameter theta is known to be at least smaller than around 10 to minus 10, which is a huge issue for the standard model. How could that be? One of the possible solutions is, in fact, the axion solution, but there aren't that many. And in fact, axion models actually aren't that great. In axion models, you would introduce an additional symmetry called a PQ symmetry. But that symmetry has to be preserved in higher dimension operators as well, or else you generate too big CP violating effects. And that's really a strong constraint. There's no reason to expect that in most models. So it's very hard to come up with natural models where you really get theta as small as 10 to minus 10, even with a PQ symmetry. Another reason to think about spontaneously breaking CP is the reason I mentioned earlier, this so-called little CP problem. Because even if you set theta bar to 0 in almost any theory where you try to explain electroweak physics, you will introduce a neutron electric dipole moment that will require some additional tuning of phases of order 10 to minus 2 or 10 to minus 3. It's not disastrous, but given that you've gone through all this work to solve the strong CP problem, it's kind of incredible that you still are going to have this strong CP phase that you can't deal with, which won't be true in models where you spontaneously break CP. Another reason I think spontaneously breaking CP might be interesting is because you exploit a natural connection between flavor and CP. Right? When you have axion models, theta parameters and strong CP is considered completely independently of flavor physics. Yet we know that the physical parameter theta bar is theta, which is a strong CP violating parameter, the coefficient of GG dual, plus the argument of the determinant of the mass matrix. So there's this natural connection with theta and the masses. So another reason to think that it might be worth looking at spontaneously breaking CP. And the final reason is the reason we gave earlier. There's no anthropic solution. So the model I'm going to talk, really I'm not going to go through the details of the model. I just want to talk about a few intriguing features of extra dimensions that make it look like maybe there's a possibility that there's a connection. I'm not 100% satisfied with this particular model, but I think there are some intriguing features of extra dimensions that makes it worth thinking harder about strong CP. So what is this model? Well, we're going to have Yukawa coupling sitting here, and we're going to have left-handed fermions sitting here. We're going to have right-handed fermions in the bulk with U1 preserving masses. That is to say, they're going to all be diagonal masses. And there's going to be spontaneous CP violation, in fact, spontaneous C violation on a brane that sits in the bulk. And that's the entire model. Okay? So that's in pictures. The worst part of the model, and this is the reason I don't really believe it, is that the left-hand fermions have to be on the IR brane. And as we'll see, that's necessary because we would otherwise get one-loop CP violation if we also try to explain flavor at the same time. We're very ambitious. We're trying to explain flavor and strong CP. And that just, you run into constraints from precision electroweak. So it would be nice to avoid that, and we don't know how to do that. I'm going to skip that. So the model is what I said earlier. We have left-handed fields on the brane, okay? We have Yukawa coupling also sitting on the brane. So let me explain the notation actually. So the right-handed fields are in the bulk. The right-handed fields, the bulk fields all have chiral partners. Those are the fields that are primes. They're not the fields of the standard model. They're the partners in the bulk of these fields, okay? So we have these mass terms, we have Yukawa terms, and we have, and these are the Yukawa terms, and we have these terms that involve the CP violating field phi, okay? So when phi gets an expectation value, you're going to introduce CP violation into the bulk quark mass, okay? That's the idea here. So the only way that we're going to have CP violation is we're going to introduce it into the bulk masses, which means it gets introduced into the wave functions for the bulk fields. And so that's what's going to communicate it from this third brane. So the third brane is where C violation happens. You want to communicate it down to the standard model. The only way that's going to happen is through the wave functions that exist in the bulk. Okay? So there's a couple of reasons that you can see right away why we might do a little bit better in addressing CP violation in this context. Okay? One reason is that you've isolated C violation from the Yukawas. So a lot of the operators that would have been very dangerous, you just can't write down because they would be non-local. They would involve the field phi, which sits here, and fields that sit there. So that's a really good thing. Another reason, which is really intriguing, is that the masses in the bulk are naturally Hermitian. That has the consequence that I can introduce a phase without introducing a strong CP phase. So let me see if I have that here. Okay. So that's sort of what this is saying here. We only have the Hermitian part of phi coupling to the fermions. Because when you work out the consequences of having a bulk field, you find it has a Hermitian mass matrix in the bulk. So let me explain why that works, why that helps. So let's just solve, this is what we saw before. We solved the equation of motion. This mu is now the full mass parameter, including the phi dependent part. But we just have an equation of motion for the field. We can solve it. This is a Hermitian matrix, which means that when I write down the Yukawa, it has a phase, but it's going to have a real determinant at tree level. For those of you who I realize this is a much more technical talk than the other talks I've given before, but for those of you who haven't thought about it, this real determinant is what you're looking for when you're looking for a solution to the strong CP problem. You want a way of introducing a phase without introducing argument determinant of the mass matrix being non-zero. And this happens naturally at tree level in this model. And this happens naturally at tree level in any model where you're getting strong CP from the five-dimensional physics. So those are really the two features of the extra-dimensional physics that I think are really intriguing with respect to solving the strong CP problem. This fact that you naturally have this Hermitian mass matrix in the bulk, so that if you communicate it this way, you naturally have it communicated in such a way that you will introduce a phase, but not a strong CP phase. And the second reason is that you naturally have things that are sequestered. You can naturally isolate C violation from where you generate the masses. Okay. And beyond that, I don't think I want to go through the details. There's some interesting flavor structure here. It works in many ways similar to what I've said before. As I said, the only problem at the end of the day is that we have left-handed fields on the brain. But this is just to say that having these extra dimensions is a really interesting way of communicating the flavor, and I just don't want to go through all of it, except to say that you can solve for all the masses and mixing angles in this case. And I think I'm going to skip all of that unless people want to know about it. Okay. So the point of this part of the lecture was to say that I think flavor physics is extremely interesting in the context of higher dimensions. There's some other things that I haven't really been emphasizing, but I think they're very important. And in fact, they're coming up in the context of B-physics that people are talking about now. One reason this is interesting is that you're naturally seeing, in some cases, sort of more interesting flavor violations in the heavier generations here. Because you naturally get connections between the masses and the mixing into the third generation with flavor violation. So a lot of the time, people have looked at flavor models that you have based on supersymmetry or based on various symmetry groups. In this case, we just have this natural connection with the wave functions, which means that even qualitatively, the predictions can be a little bit different. And so I think people are just beginning to really think about what the flavor consequences are. And those are true, those consequences apply both at low energies, where you might get interesting effects in the B system, and at high energies, where you might see, for example, flavor changing top decays, which would be extremely interesting. So there's a lot of different qualitative consequences of these models, which is one reason to think about it. Another is, people have been thinking about flavor physics for a long time and trying to get it through symmetries. And it's actually very difficult to get this natural connection between the angles and the masses. You can do it in some cases, but it's much more artificial looking. Here, as I've tried to emphasize, it really comes out as an automatic consequence of the wave functions, which is extremely compelling. And the fact that the flavor violation from the KK gluon was much smaller than we anticipated is also really intriguing. The fact that you really have this very flat gluon wave function in the UV. really suppresses flavor violation almost to an adequate extent, even without doing any work. And with a little bit more work, that is to say with some sort of gym mechanism built in, you can really get the scales to be quite reasonable, that you really get rid of even those potentially dangerous ones. So there's really quite a lot to look at. In the case of CP violation, as I said, there are these two features that make it intriguing to think about whether you can really solve strong CP by spontaneously breaking CP in the bulk. We know people have thought about spontaneously breaking CP before, but they really have a natural connection with flavor, and also you have to introduce these very high scales. Here, our scale is relatively high, but it's much lower than any of the scales that people ordinarily have to introduce to get away with this. And again, it's because there's such strong flavor structure built in, such strong symmetry structure built into a lot of what's going on in the extra dimensions. So as I said several times, I think one of the reasons this is interesting is we can really naturally get this exponential hierarchy. We can naturally get the KM angles, and we can potentially use sequestering to address strong CP problem. And so I think there's still some other very interesting questions to ask. Does this naturally come out of explicit realizations? As I said, I think there's a lot of interesting flavor physics to still study, especially now as B physics and D physics becomes much more constrained. And also, I think it's going to be interesting to think about flavor changing processes in the future at the LHC. So I'm going to say a few words about other things afterwards, but I'm going to conclude here with this part of the talk. So I'm just going to stop for questions. It's hard giving talks right after lunch. Yeah. Sure. Sure. So just qualitatively, before we look at the slide, why are there precision electroweak issues here? Well, the reason is we have gauge bosons in the bulk, okay? So suppose you have the light fermions sitting on the IR brane at the TeV scale. That means that you can have KK modes of order TeV, which interact with your light quarks, your light leptons. And so they can be exchanged and generate corrections to not just the ST parameters, but just to any interaction involving the light quarks, so Z to EE. Okay, so, and which is, as you know, is quite well constrained. So if you have the light quarks sitting in the infrared, you will get diagrams that generate various precision electroweak effects. So, for example, you can have a Z boson mix into a KK boson with some Higgs expectation values that then decay to FF bar, and that's going to be a correction to Z to FF bar. So that's one constraint. You can also get contributions to the T parameter, because you could have W3 mixed with a KK boson, which then goes back to W3, which again can give you some precision electroweak stuff. And as we know, that's just very constrained. So that's good. So if you really apply those constraints, you're getting the KK modes up to around 10 TeV at least, because it was so low. See, an advantage of a lot of the flavor models is that generally speaking, what they do is because light fermions are light, they get localized away from the TeV brane, which is where the KK modes sit. We talked about this in the previous lecture, but the KK modes that are a TeV scale are sitting in this IR brane. They're sitting in the same region that the Higgs is sitting in. So the light fermions should be sitting away from that. So to the extent that light fermions have wave functions which are localized away from where the Higgs sits, they're also localized away from where the KK modes sit. So they're going to have a much smaller interaction with the KK modes than you would if the light fermions were localized nearby. And that's the way that you generally can get completely adequate suppression of precision electroweak things. The strongest constraints ends up being from the B quark, because you need the top quark to be heavy. So the top left has to be somewhat near the IR brane, which means the B left has to be somewhere near the IR brane. And that ends up being the strongest constraint in those models. Yep. When you put what? Mm-hmm. Yeah.
So what is the rule of writing? You have a lot of freedom. There are new interactions that you can write, like choice sign terms, which are the same dimension of the
Yeah, so you can include those terms, and they're not really affecting anything. I mean, they amount to... It's a non-renormalizable theory, but you can just work... So basically you put in the constraint that you can't have a strongly coupled theory. So that puts a bound on what your coupling is. That's one constraint you get. So you don't want it to be too strongly coupled. So that just puts a constraint on the size of the extra dimension. The Trent-Simons terms, we thought about it, particularly in the context of strong CP, but they don't do anything because once you... Essentially, you can show that it basically amounts to brane terms in these models. That you can use the equations of motion to any CP violating effect can be turned into boundary conditions, essentially because it's a total derivative. So it turns into, so as long as you don't have CP violating effects on the branes, you're fine. So they don't turn out not to be dangerous in these models, but they were potentially worth thinking about. Okay. Other questions? Yeah.
Have you any suggestions for the neutrino oscillations? That's one of them.
Yeah, in fact, my collaborator Gilad Perez and I are in the process of not finishing a paper at the moment. But we actually do have ideas about neutrino oscillations, and it's actually really nice because what did I show in this particular talk? I showed that the angles are naturally connected to sort of the square root of the masses, because there's this big hierarchy of masses, which we explained by the product of the left and right-handed wave functions. In the case of the neutrinos, they're actually amazingly degenerate to the extent that we know. Of course, we don't know the lightest mass, but at least in terms of the mass splittings, they're quite similar. So if you actually had an SU3 symmetry on the left-handed neutrinos, and you got the entire hierarchy of neutrino masses from right-handed neutrinos, exactly the same argument that I gave to explain why you get KM angles small related to the square root of masses would actually tell you that the KM angles are naturally big because they're just that original V matrix. If you don't have hierarchies in F left, that is to say in the wave functions of the left-handed neutrino fields, you would naturally get order 1 mixing angles. So we have a model where we don't precisely predict one, but we predict angles to be naturally big. And that seems to work quite well. Is that fair? Okay. No, it's really, I mean, I actually think that's another interesting feature because there just aren't that many really nice models of neutrino masses. And in this case, I mean, we would sort of have qualitative predictions at the very least. We wouldn't expect the 1,3 angle to be extremely small, although it could be somewhat smaller. So if we found the 1,3 was really small, this would probably really say that model wasn't right. Okay. Other questions? Okay, so I'm just going to say a few concluding words since I have an audience. So I mean, I think so. I concentrated primarily on RS in these 3 talks, and the point I've been trying to get across several times is that it's very nice to do these searches that people have been doing for a long time. But I think as we think more, and I think there's a workshop going on now. There's a lot of interesting phenomenology associated with the RS model, but associated with other models as well. And so we can't just assume we know what we're going to see at the LHC in advance. We really want to be thinking about what are the possibilities and what are the ways we're going to distinguish among the different models. And what we've found is that, of course, we want to do all the standard searches people have talked about, but we also want to make sure that for any model that we can really get top quarks to maximum possible energy. We want to do compositeness studies, flavor changing in the top sector. I mean, something I did not have time to talk about for people doing Higgs physics. I mean, one thing that I found amazing is if you have a 2 Higgs model, one of the really interesting things to measure is going to be actually the ratio of the branching ratios into the modes that we can see, namely tau tau bar and gamma gamma. And it turns out that in 2 Higgs models, if tangent beta is like order 10 or so, you can get enormous effects in the ratio of branching ratio. That is to say that that ratio can change from factors of 2 or 3 from the standard model. You can have you can have Higgs to BB bar increased by factors of 2, decreased by factors of 2, or even more. There can be really enormous effects. So there just are all these kind of hidden gems of interesting physics to do. So, and it's really important to think about those as well. Like, how well will we be able to measure those branching ratios? What I'm saying is that even if you could just do, an order 1 measurement, it's actually an interesting measurement to do. So I think there's a lot of interesting physics that remains to really be thought through. I think a lot of the flavor physics in this case is going to be very interesting. And really thinking about ways to identify these energetic tops, I think is a really important challenge. So I think this is a very exciting time. And I think the real tragedy would be if there really is interesting stuff there and we're just not ready to find it, that we throw away interesting data. So I think that's one of the reasons we as model builders are doing these models, because we want to see what are the signatures. But even in models that have been around for a long time, like 2 Higgs models, there are these really interesting physical consequences that people haven't really been focusing on. So I think there's just a lot of interesting work to do. So good luck.
So are there more questions? Please.
Can RS2 scenario can do the same thing? For example, the CP violation and the heresy. I mean that the RS2 scenario can it do the same thing?
Okay, so the question I believe is about
today?
RS2.
Yes.
So RS2 has to do with just having an infinite extra dimension. And I haven't talked about RS2 in these talks because on the whole, there aren't that many consequences for weak scale physics. The only case where we can connect it to weak scale physics I mentioned briefly, which is if you have another brane in the bulk. That's the weak brane, that's not the boundary of the space. And so in that case, you can try to do a lot of the same things that we've done, but the phenomenology of the KK modes are different just because you have an infinite extra dimension. But aside from that, the general mechanisms would be the same.
See. Thank you.
Sergio?
One of the reasons of pointing this supersymmetry was the sort of heavy problem. Suppose supersymmetry will not be found at LHC. I think supersymmetry still need a big symmetry, which applies to the symmetry of space and time. I have, the symmetry Planck scale that is much higher.
Yeah.
Than what is the Planck scale. Now, what I'm asking is the original motivation of this work scenario was to explain the kind of equation, and suppose that these spectacular signals are not found. Are there some other applications, or is it really ruled out?
Yeah, I mean, I think you can sort of say similar things that you can explain different mass scales. And in fact, one thing we're looking at, this is way too early to say it, is applying it in the context of supersymmetry. And in the context of supersymmetry, it could be that your IR brane is at a much higher scale. And it could still, because as you know, we don't have really great models of supersymmetry breaking. So one example where it might apply is, in fact, in a supersymmetric context, where you could explain low scales through supersymmetry, but it could help explain the supersymmetry breaking scales. So there's examples like that. Basically, any theory that involves other scales, there are potential applications. And also, I mean, if we forget about solving the hierarchy problem, it solves the strong CP problem. I mean, the only thing that was bad in that model, which I didn't go through the details of it, is that the scale was constrained by Electroweak constraints, so it's a 10 or 15 TeV. If I don't want to solve the hierarchy problem, there's no problem with that, and I've solved the strong CP problem in a fairly elegant manner. I mean, the reason that model was so constrained was I was really trying to do everything. We were trying to get the hierarchy, we were trying to get quark masses, and solve strong CP. There are not many models that do that. And it comes awfully close. So if you had some other way of addressing precision electroweak, you would get everything in that model.
So do we have more questions? No, I don't see any. So last time, speaker again. Maybe see you some other time.
Yeah.
We'll be talking about, we have
Some data. There we go. That would be exciting. Yeah, that would be very exciting. Yeah, that would be great.
Guess before.
Yeah.
So, everybody,
Watch it.